Today we're going to talk about the Equational Theories project. This is massive online collaborative project with, again, over 1,000 contributors, probably more than that. So we can't talk about every single thing that has been going on in the project. Hence why we're going to focus on one very specific contribution, the one we're most familiar with because we are directly involved in it. So here's the outline of the talk. First, I'm going to describe the Equational Theories project for anyone who hasn't heard of it, or maybe you need a refresher. In the second part of the talk, I'm going to introduce you to meta-theorems. This is this collection of results which are very interesting, and by their nature, they're also quite tricky to formalize, and hence why Anand's going to tell you in the last part of the talk how to do that in Lean. Okay, so what is the Equational Theories project? This all started over a month ago as an idea, a blog post by Professor Terence Tao. In order to understand the aim of the project, we need to review some basic universal algebra. And the main object here of the study is the magma. So a magma is just a set with a binary operation. And we do not assume anything about the binary operation. So maybe it's associative, maybe it's not associative, maybe it's commutative, maybe it's not commutative. And the aim of the project is really to understand magmas. But it's really hard to say anything interesting about magmas in general because they lack a lot of structure. So what we do instead is to study them under certain conditions or laws. So for example, the associative law, the commutative law, these are all examples, idempotency law, these are all examples of laws that magmas that you find in the wild might satisfy. And I want to be very specific about what I mean by a law here. So a law is just going to be some equations. I'm going to use the terms laws and equations interchangeably, but Anand's going to be more careful to make the distinction. So for me, a law is just an equation involving some variables. Yeah, so an equation involving some variables, involving a binary operation, and that are implicitly universally quantified. What that means is that when I say a magma satisfies this law, all that means is that for every possible substitution I can make, if I take elements of the magma and I substitute them in place of the variables, then the equation should remain true. And that should happen for every single substitution. Okay, so that's what it means for a magma to satisfy a law. And the aim of the project is to understand magmas, laws, and the relationship between different laws. And the most important relationship is implication. So given two laws, A and B, it makes sense to ask whether A implies B. And that means that all magmas that satisfy A also have to satisfy B. That's it really. So given any two laws, A and B, can you provide a proof of whether A implies B, or can you provide a counterexample? That would be a magma that satisfies A but doesn't satisfy B. Of course, you can't do this for every single possible pair of equations. First of all, because there are infinitely many. And actually, there's no algorithm that given two laws A and B, it will tell you whether the implication is true or not. It just happens to be one of those undecidable problems. So what we actually do is to set some arbitrary constraint here. So I think for the actual project, the constraint was we're going to consider equations that have the binary operation appearing at most 4 times. So then you end up with a large but finite set of equations, and then you can ask, okay, for every single pair of equations here, either prove that A implies B, or prove the anti-implication that A doesn't imply B. And for this particular project, right, I think the number of equations comes out to be around 4,000, maybe 5,000. And if you work out how many implications that gives you, there'll be around 4,000 choose 2. It's around 20 million. And the sheer size of it, I think this is what makes this project really special, unique, one of its kind. Because if you compare it to other online collaborative projects that in mathematics, I think most famously the polymath projects, the output of a polymath project is still a paper in the traditional sense. So even though you needed a large number of mathematicians to come up with the results, the output can be checked by a small number of mathematicians, relatively small. In this case, though, the output is 20 million theorems. So not a small number of mathematicians nor a large number of mathematicians can check this in a reasonable amount of time. So if you require that enter interactive theorem provers, if you require that every contribution is made through something like lean, then the issue of trust disappears completely. And everyone is doing correct mathematics. Okay, so that's more or less what the project is about. There has been so many contributions, a lot of people. I cannot tell you all the cleverness, all the things people have tried to chip down at these 20 million members.
Just a question on so you're looking at just unary implications in one equation and another one. Right? You're never trying to look like whether this combination of 2 or 3 different equations might imply a third one.
That's a good question. And this is one of the most natural questions that you can make. I'll talk about this more later. Yeah. But that's a good. It was actually a topic of discussion in the early stages of the project. Okay. But yeah, about this. Yeah. So a lot of the contributions have been focused on trying to prove the trivial implications quickly using automation. Also some use of artificial intelligence that can output some lean code that makes some sense. Also, if you have a finite magma, you can encode this multiplication table, and then you can check systematically whether this magma is a counterexample to any of the implications that you have to prove. So lots of things going on. In this talk, we're going to focus on one very specific one, which is meta-theorems. Thanks. Right, but to tell you about meta-theorems, I have to tell you about balanced equations. I want to provide the simplest example of the phenomenon I'm really interested in. So I'm going to call an equation balanced if for every variable that appears in the equation, it appears the same number of times in the left-hand side and the right-hand side. So in here, x appears 2 times on the left-hand side. It also appears 2 times on the right-hand side. Y just 1 time. Z just 1 time. So if that happens for every variable, we call the equation balanced. In the early stages of the project, I was toying around with balanced equations because I noticed they satisfy this very interesting property, which I'm going to call meta-theorem 1. Which is do not imply non-balanced equations. I should say something about the name meta-theorems. It just boils down to the naming convention of the project, right? And a theorem is a result pertaining to a specific equation. So equation 2 implies equation 47. Equation 13 doesn't imply equation 14. Things like that. Those are theorems. Meta-theorem would be something that pertains to many different theorems at the same time. So you can get a lot of theorems from a single meta-theorem. And you can see this in this case, right? So if you imagine like the set of all balanced equations. And its complement, the set of all non-balanced equations. Then you get a lot of theorems that say the balanced equation, this balanced equation doesn't imply the non-balanced equation, this doesn't imply this doesn't imply this, etc. Okay, so pretty short, sweet, powerful. How do we prove this, or why is this true? I'm going to give 2 proofs One is going to be the syntactic proof, and the other one is going to be the semantic proof. The syntactic proof is like the one that came historically first, so maybe we'll start with that. Yeah, so the idea syntactically is you do a proof by contradiction. You start with a balanced equation here in the balanced equations. And then you have a non-balanced equation over here. And then you assume for the sake of contradiction, okay, imagine a balanced equation implied a non-balanced equation, then there must be a proof of this. So proofs are finite, so you can do induction on the proof length. You can basically induction on the proof tree. So okay, there are some steps here. It's finite many steps, so you can do some sort of induction. And the key insight is that if you start with a balanced equation, like the one over there, no matter at some point you're going to have to use that equation in the proof. So, but when you use the equation, you're going to have to substitute in something. Whenever you substitute in something into a balanced equation, like I'm going to replace x with something, some combination of variables and other and the binary operation, then I'm going to have to do it the same number of times on the left-hand side and on the right-hand side. Hence, the equation is going to remain balanced. You're never going to break the balance. So throughout the whole proof, you're going to end up with balanced equations. So you can never get something that's non-balanced at the end. Hence, that's a contradiction. Okay. Yeah, it's a proof. It's good for a first proof. I remember I shared this with the other collaborators, and I remember waking up the next morning and noticing that Professor Tao had taken all of this, which is, it's a bit messy, I admit it, and came up with a one-line proof of this result. I was a bit scared, but delighted, So let's do that. This is going to be the semantic proof. Notice that we're proving a lot of non-implications here. So we're saying this equation doesn't imply this equation, but we haven't actually given any counterexamples of any sort. We're trying to be clever. We're analyzing the structure of the proof, the structure of the equations. It's purely syntactical. Semantics would be to provide an actual counterexample. And the counterexample here is quite simple, actually. So the proof, the one-line proof would be something like, consider a magma real numbers under addition. Okay, maybe this needs some more explaining. So the real numbers under addition, the claim is that they satisfy all balanced equations. And you can see that, right? Because the key is that the real numbers under addition are associative and they're commutative. So when I present to you a balanced equation, you can basically ignore all parentheses because of associativity, and commutativity says that you can group the variables together. So, I mean, if you with that balanced equation, or with any balanced equation, you will basically end up with something that looks like 3x plus 4y is equal to 3x plus 4y, exactly because it's balanced, right? You're going to have the same number of variables here and here. So that balanced equation is going to translate to this. So this magma over here satisfies all balanced equations. But it doesn't satisfy any non-balanced equations by the same reasoning, right? A non-balanced equation would look like 2x plus 7y is equal to 3x plus 4y. And this is not going to be true for all values of x and y. Okay, so if that would be the end of the story, then I probably wouldn't be talking about this. But the point here is that there are actually many similar results, and they're all not so trivial. And it's quite hard to pin down where they're coming from and what the pattern is to these results. Okay, so I'm going to give another example here. Oh yeah, balanced equations modulo n. You can probably guess by the name where this is going, but it's basically an equation is balanced modulo n if for every variable it's going to appear the same number of times in the left-hand side and the right-hand side modulo n. Just stick the modulo n at the end. So this is an example for n equals 2. Know that x appears an even number of times on the left-hand side, and on the right-hand side, y appears an odd number of times on the left-hand side, on the right-hand side. Z doesn't appear at all on the left-hand side, but 0 is an even number, so we're still good, I think. Yeah. The meta-theorem that's related to this actually is that it turns out that balanced equations modulo n do not imply non-balanced equations modulo n. And that will be our meta-theorem too. I'm not actually going to write down the proof. It's very similar to, I mean, again, there are two proofs. You can do a syntactic proof and a semantic proof. The syntactic proof is very similar. The semantic proof is maybe something that will give you something to think about when you go home. Yeah, let me give you another example. Of a different flavor, because it's not all about balanced equations. There's something else going on here. Oh yeah, equations which agree on the leftmost variable. So these are equations of that form. X times some rubbish is equal to X times some other rubbish. Name is pretty self-explanatory here. What would be the meta-theorem here? Well, I'm just gonna tell you. It's gonna be the equations. Okay, I'm not gonna say that. I'm gonna say good equations are equations in which agree on the leftmost variable. So the meta-theorem is that good equations do not imply non-good equations. Bad equations? So actually, let me give you a syntactic proof here because it's actually quite nice. It's easy to see why this is true. So it's the same setup as this. So you start with a good equation. So x times some rubbish is equal to x times some other rubbish. And by the sake of contradiction, assume that you end up with something that's non-good. Then at some point you're going to have to use this equation. You're going to have to substitute in something. But the point is that if you substitute in the rubbish, you're going to still get rubbish. So that's fine. The equation remains good. And if you substitute in the x here, then the leftmost variable is not going to change because you're going to have to do it to both sides. And the new leftmost variable is going to be the leftmost variable of whatever you're substituting in. So again, having the same leftmost variable is invariant under substitution. It's invariant under the whole proof. And yeah, I will give the semantic proof later. What are we doing on time?
You still have 30 minutes. And then 10 minutes.
Okay, 30 minutes. Okay. Yeah, so I suppose the aim with these examples is to get you thinking about what is the more general pattern here. What's going on? Is there some way to systematically list all these meta-theorems? Or just study them in some sort of systematic way, get some general framework. And that's what I'm going to talk about today. The category theory disclaimer is that this can get very category theoretical. If you like that kind of stuff, maybe ask me about it afterwards because I'm not going to go into it right now. I'm going to try to keep this talk category theoretic free. And okay. I'm going to ask you to consider an equation, say the associative law, for example. And I'm going to ask you to consider all possible consequences of the associative law. Right, so that's just going to be a set. We have the associative law over here. And consider the set of all possible consequences, all equations that are implied by the associative law. And the thing to notice is that this set, this giant set, is closed under implication. It's almost trivial, so it's by definition, right? But if you frame that in the negative, that means that everything inside the set cannot imply something outside of the set, right? Because if it did, it would have already been in the set, right? So this is, you have the set of all things that are a consequence of the associative equation. Then anything outside the set, that you cannot have an implication that goes like this. Basically, that's all I'm saying. And it follows this pattern, right? So you have some set of equations do not imply anything in its complement. And this, if you like, is the meta theorem. I hope that doesn't make things more confusing, but this is actually how I think about it. It's the thing that allows you to get, it's the template for the meta theorems. So, yeah. You can actually do this for the associative equation, actually. So what is the set of all things that the associative equation implies? Well, it's going to be equations for which parentheses, if you ignore the parentheses, are basically the same equation. So we've all learned that associative means that I can basically ignore parentheses, right? So if I have an equation that goes like, I should prepare an example here. And maybe it's a bad example. Yeah, so basically you have something, anything that looks like this, like it's kind of like the same equation, only the only thing you've done is rearrange the parentheses. So that would be a consequence of the associative law, and everything that is a consequence of the associative law kind of looks like this. So the new meta theorem here is that equations in which that agree on equations that have the same list of variables are sort of invariant under some kind of substitution or proof. These sorts of equations cannot imply equations outside these sorts of equations. Yeah. Okay. And if you want a semantic proof of this fact, you can think about the free monoids of in the alphabet you're considering. The alphabet, by the alphabet, I mean the equations, the variables that you're considering. If you consider, in this case, like you have set x and y, you consider the free monoid on x, y, and z, then this monoid is going to make this equation true. And if you consider any equation that doesn't look like this, the free monoid is going to make it false. So that free monoid is going to be your counterexample here. Okay, yeah, and left projection, which is this equation, by the way. So for all x and y, x dot y is equal to x. That will give you the consequences of that law is basically the set of all good equations that we were talking about earlier. So equations that agree on the leftmost variable. Because you see that law kind of implies that whenever you have a multiplication, you can ignore everything that's on the right, and you're going to end up with the thing on the left. And if you do that many times, any equation is going to reduce to just what was on the left in the first place, so the leftmost variable. And yeah, the meta theorem is meta theorem from earlier. And semantically, actually, I'm going to skip the semantic proof just in the interest of time. Okay. This is going back to the question that you had earlier. So it turns out it's very nice to expand the language in any way that you can. So, and the motivation for this is that the first two meta theorems about the balanced equations and then balanced equations modulo n, they don't really fit this general pattern of just consider one equation and consider all consequences of it, right? I challenge you to come up with an equation that has as the set of all its consequences just the balanced equations. It's a bit tricky to do. Much more natural, in some cases actually necessary, it's not just more convenient. You can think of, instead of considering consequences of a single equation, you can consider consequences of a group of equations. In this case, what if you consider all consequences of the associativity and commutativity law combined? Right, so what's that going to give you? It's gonna give you basically, you can ignore all parentheses by associativity, you can move things around by commutativity. And so you're gonna get basically the balanced equations, right? Equations that agree, like the only distinguishing feature, or they're gonna have the same kind of multi-set of variables on the left-hand side and the right-hand side. So yeah, the meta theorem here would correspond to the balanced equations we were talking about earlier. And yeah, semantic proof. You should skip.
And to the K.
Hmm?
Oh,
Oh yeah, and to the K. Thank you. Yeah. Yeah, I should do this actually because Anand's gonna use this. Let me know if I okay.
Time's good.
Okay. So I already gave you a semantic proof for the balanced equations things, but it turns out like if you think about that one-line proof, it's really good, but it actually doesn't use at all the fact that we're dealing with R here, the real numbers, right? We haven't used the structure of the real numbers at any point. So there should be some more natural, a minimal counterexample for this thing. And it's like the least amount of linear algebra that you need on your magma to be able to carry out this proof. And if you think about it, what you want is a magma that would be the natural numbers, list of natural numbers, say to the t, under addition. And okay, this is a magma. So this is list of natural numbers under pointwise addition. And this is kind of like the free magma generated by associativity and commutativity. So it's kind of like the least amount of things that you need for this to work. And the claim is that this thing is a counterexample. That means it satisfies all balanced equations, but it doesn't satisfy any non-balanced equations. And you can check this on the generators, right? So by generators, I mean things like, the standard base, basically. Okay, cool. It turns out you can actually, you actually want to expand the language even further because it's kind of funny, right? Because you're only considering equations. So you don't know anything about, if you think about it, your logical system is quite poor. You only have equality, some implicit universal quantification, and that's pretty much it. But notice that how adding more logical symbols, even it seems like it makes things more complicated, but it actually gives you tools to investigate the bare bones equations that you're interested in. So conjunction is pretty useful, and constants are really useful as well. So now I'm going to give the example of the balance modulo n reframed in this context. So it would be think about the conjunction of associativity, commutativity, and imagine you have also a symbol, which I'm going to denote by 1. And I'm going to, do the usual thing that x1 is equal to x. That's what I mean by unity there. And I'm also going to say x to the n is equal to 1. And if you think about the set of all consequences of that conjunction of equations, say, you're going to get exactly the equations that are balanced modulo n. And the semantic proof is very similar to this one. So that's exactly proof. The semantic proof is very similar to this one. But instead of consider the natural number, list of natural numbers, you're going to consider that modulo n, list of set modulo n kind of things. So this guy will satisfy all balanced equations modulo n, but won't satisfy any non-balanced equations modulo n. I think that's it. So I'm gonna pass over to Anand now. Thank you for listening.
Thanks. So in this half of the talk, I'm going to be talking about how the theory of meta-theorems and all the theory we've discussed so far can be formalized in linear. So I'll start by talking about equations and laws, because that will be relevant for what's to follow. So here's the fundamental dilemma. So we have equations which we can define in B. So a typical equation might look something like x circle y equal to z circle x or something like that. But a meta-theorem, fundamentally speaking, involves reasoning about the syntax of an equation. So for example, if we want to tell whether an equation is balanced, we need to look at the multi-set of variables on both sides of the equation. And this is fundamentally a syntactic construction. And this kind of reasoning is difficult or maybe outright impossible to do in Lean. And so we need to sort of carefully work our way around this constraint and figure out how to set things up to make this kind of reasoning possible. To give an example of what I mean, consider a definition that looks like this. So we're defining a natural number n, and we're defining it as 1 plus 2. Now let's say we want to prove that the number n is defined as a string whose length is 5 characters long. I claim that it's impossible to do a reasoning of this kind. And the reason is, if we consider 1 plus 2, and we're able to prove that it has length 5, then we can also prove in our system that 1 plus 2 is not equal to 3, because this has a string length of 5 and this has a string length of 1. So we actually get a contradiction if we're able to do reasoning of this sort. So we need to go beyond the object level reasoning, and we need to somehow get access to the syntax of the underlying equation. And if we have access to the syntax of the equation in a convenient form, such that reasoning about the syntactic version of the equation can be transferred over back to the equation itself, then we have a way of proving the kind of meta-theorems that we've seen before. And this is the kind of rough strategy that we adopt. So before I go ahead, I'm going to say something about equations and laws, and I'm going to draw a careful distinction between them. So by an equation, I mean something like this. A typical equation you would see in the project is something like this. So equation 953, you have the left-hand side, you have a right-hand side. Both are defined in terms of symbols. They only involve the magma operation, and all variables are universally quantified. Internally, this expands into a definition that looks like this. So it's basically the same thing, but now the quantification is explicit. And it's also saying that this holds generally across magmas. And so this is what we mean by equations. And equations are the fundamental objects we deal with. The equations are the things that we prove theorems about, and which basically form the nodes of the implication graph that we're trying to construct in this project. But on the other side, we can also define what are called laws. So laws are kind of like the syntactic counterparts to equations. So the law looks pretty similar to the equation we started with. So this is the equation we started with, and this is the law. So instead of variables here, we have these variable numbers. But the key distinction is that a law is actually a tree. The two sides of the law are actually trees. And these trees like fundamentally capture the syntax of the encoding of the equations. To make this more concrete, I'll draw these trees out. So this is the left-hand side. So yeah, these laws are actually trees. And what we see over here is actually a representation of the tree structure. And we have access to this tree structure, which allows us to do the kind of syntactic reasoning we need to prove the meta-theorems. And regarding a bit about the implementation. So laws are actually defined as ordered pairs of elements of the free magma over a given alphabet. So the free magma is basically the smallest magma that contains one, the elements of the alphabet, and two, for any given two given elements of the free magma, we can construct a bigger one which is basically the tree that has these two as children. And so essentially, like objects of the free magma are trees that look like this. And these are the trees that we'll be using to reason about the syntax of the equations. So to sort of summarize the strategy we're going for, we're starting with an equation. We want to generate a law out of it. A law is a syntactic counterpart to the equation that captures the tree structure of the equation. And we also want to say that when we prove that the law, when we prove that a magma satisfies the law, we also want to be able to deduce the fact that the same magma satisfies the equation from which this law was derived. So here's how we can define the satisfiability of a law in a magma. So let's say we have a law that looks like this. So we call a map an evaluation when it sends each of these variables to corresponding elements in a map. So this map over here would be an evaluation, and this is a law. And then we say that the law satisfies the evaluation if when we map the left hand side under the evaluation and the right hand side under the evaluation, we get the same result in the magma we're targeting. And in general, we say that a magma satisfies a law if it satisfies every such evaluation, every possible evaluation. And now I'll get to the part that I was talking about earlier. Oops. Oh yeah, never mind. Yeah. So now I'll get to the part I was talking about earlier, where we first want to generate the law from an equation, and second, we want to generate a proof that the law is equisatisfiable with the equation we started with. So we do this in two steps, and both steps involve modifying the equation command that's used in the project to actually define equations. So here's what a typical definition of an equation in this project might look like. The equation command, being a command, has access to the actual syntax underlying the expression that's being defined. And with a bit of metaprogramming, it's possible to extract the underlying law corresponding to the equation that we're defining. So this looks like the equation. So this is the equation that's automatically defined. And what I wanted to show was the law, which can be automatically generated from the equation. The hard part is then generating a proof that satisfiability of the law is equivalent to satisfiability of the equation. So how do we do this? We can do this in a couple of steps. So here's the equation. So with a bit of metaprogramming, we can get the law out of it. So this is by modifying the equation command, which is used to define the equations. And now, given the law, and let's say this is over a finite alphabet. What we want to do is to generate an equation from this law such that an assignment of values to the universally quantified variables in the equation corresponds to giving a substitution for the law. Like a substitution is a map from the variables of the law, like from the alphabet of the law to a magma. So basically, there's correspondence between substitutions, like associated with the alphabet of the law, and assignments of variables to the universally quantified variables in the equation. So to wrap up a bit, so let's say we have a law, and then let's say the law is over a finite alphabet. We can construct an equation from the law that is equivalent to it. And this equation turns out to be equal because of the way things are set up. It turns out to be equal to the one we started out with potentially after unfolding definitions. And then we can also go a step further and extend this law to a larger alphabet. And this entire setup going from the equation to the law, proving that the law compiles down to a certain equation which is equal to the one we started with, and then extending the law to a larger alphabet gives us the equivalence that we want. And that's the one we work with. Over here, we're actually dealing with two different sets of alphabets for two different reasons. So this law is defined over a finite alphabet because that makes this entire proof go through easier. So it has a finite alphabet, so it's equivalent to an equation with a finite number of quantifiers. So that's the reason we go through this part of the setup. But then later we extend the alphabet from a finite set to the set of natural numbers. Because then all laws that we're dealing with are defined over the same set, which is namely the set of natural numbers. And that makes it easier to compare them, to prove implications or non-implications between them. And that's the basic setup. And what we've done so far is that every time we define an equation, we're also defining a law, which is its syntactic counterpart. And we're defining a proof, we're also producing a proof that every time we prove something about the law, every time we prove that a magma satisfies the law, then it's also true that the same magma satisfies the equation from which this law was derived. Right. So the overall objective of this project that we embarked on was to prove certain kinds of anti-implications. So in other words, we want to find equations like let's call them equations A and B, such that A does not imply B. In other words, we want to find a magma in which A is true, but B is not. So the entire process of finding or like proving anti-implications boils down to finding certain magmas where we can prove that A is satisfiable, but B is not. So in turn, it boils down to a question of deciding when an equation or when a law is true in a certain magma. If the magma has if the magma has infinite size, then in general it's hard to decide when a certain law is satisfied in the magma because this involves infinitely many checks. But it's possible to come up with certain kinds of nice magmas where the general question of satisfiability is equivalent to checking whether a specific substitution for the law gives equal elements in the magma. And this might have been a little abstract, so I'll go through a couple of examples of what I mean. We've seen these examples already in the context of what Hernán explained, and then I'll go to the final bit of implementation. Right. So, for example, let's consider lists. So lists are a magma where let's fix an alphabet alpha. So lists over this alphabet form a magma where the magma operation is concatenation of lists. And let's say we have a law that we want to check for satisfiability over this of type alpha. So if alpha is non-empty, then there are infinitely many lists over alpha. I mean, even when alpha is empty, I think. When alpha is not empty, there are infinitely many lists over alpha. So checking whether a law is satisfiable over this is not possible to do directly computationally. But what we can do instead is to evaluate on a specific set of elements. We can evaluate on so let's say our equation is the associativity axiom. So and we want to check whether this holds in the magma of this under concatenation. So rather than checking it directly, which is extremely hard since this is an infinite set, what we can do is substitute in very specific lists for each of these variables, and then check whether that substitution gives us gives us something that's true. So for the variable x, we substitute the singleton x. For y, we substitute the singleton y, and similarly with z. and both sides give us the list X, Y, Z. So basically we've the summary of what I've said so far is that checking satisfiability in this is equivalent to checking satisfiability for a very specific set of elements, namely the singletons. This will be more clear in the next example of multisets. So essentially, let's say we have an equation. Let's consider the same equation again, and we want to check whether, for example, we want to check whether both sides have the same multiset of variables. So what we can do is consider the magma n to the d, or n to the 3 over here, since we're dealing with 3 variables, under addition. Checking whether this equation is true in this magma, in general, is quite difficult. But what we can do is we can substitute in the basis vectors for x, y, and z. And then plug those in over here. On both sides, we end up with the vector 1, 1, 1. And because these basis vectors generate n to the 3, we actually know that it's true in n to the 3 by verifying on these 3 basis vectors. And similarly with left and right projections, we just substitute in the specific values and then evaluate. And that's sufficient to tell us whether the equation is true in the general magma. And in general, we can abstract. So if in general, our strategy is we want to find a magma for which it's easy to decide whether a law is true. So we can capture this in a concrete definition like this. So roughly what this is saying is, oops, hang on. Yeah. So roughly what this is saying is that if we want to verify that a certain law is true in a magma from this family, it's sufficient to just verify it for a specific substitution of variables into the law. So that's a theorem you can prove about magmas of this class. And all the examples that we've seen so far are examples of the class that is defined here. And now on to the results. So to summarize this, the first part, we basically started off with an equation. And from the equation, we've generated a law, together with the proof that satisfiability of the law in a magma is equivalent to satisfiability of the equation in a magma, in the same magma. And in the second part, we've isolated a certain class of magmas where the question of satisfiability of a law is sort of made simpler by the fact that there's a specific substitution such that if we verify the law on that specific substitution, then it holds true in the magma generally speaking. So like in the n to the 3 case, it's sufficient to verify whether an equation true is true, equation in 3 variables is true on the substitutions x equal to 1, 1, 0, 0, y equal to 0, 1, 0, and z equal to 0, 0, 1. And once we make the substitution, and if the substitution gives a correct result, then it's true that the equation is true of the magma more generally. And once we have a magma family of this sort, it's possible to generate a whole bunch of non-null equations. So let's say we have a magma family of this sort. Then for each equation, we can decide whether or not it's satisfied by the magma. And for any equation that is satisfied, and for any equation that's not, we can use this magma as a counterexample for the implication that this equation implies that equation. So in other words, once we have a magma where it's easy to decide whether a law is satisfied in it, we can generate a whole bunch of examples by going through the list of laws that don't apply other laws. And to give an idea of what I mean, I will open up the code. So in the list example, so we end up with a bunch of examples like this. So we have, for example, equation 1 up here and equation 3, 4, 5, 1, 6, 9. And we can basically automatically construct a magma for which equation 1 is true, but equation 3, 4, 5, 1, 6, 9 is not true. And the general flavor of the counterexample over here is that it's, so this is in the list family. So the general flavor of the counterexample here is that it's a certain kind of list. So we're considering lists of natural numbers under concatenation. And the general flavor of the results in this file are that the counterexamples are all like multisets of natural numbers. And these equations have the same multisets of natural numbers on both sides, while the things on the right hand side do not. And yeah, similarly with left projections and with right projections. And in all, like, so this constitutes something like 300, like order of 300 or 350 non-implications in total. And once we take the transitive closure and various other kinds of closure operations, we end up with something of the order of 12,000 equations in total, generated by counterexamples, which in turn come from meta-theorems like the one over here. And yeah, that more or less concludes our contribution to the project. And yeah, we can take any questions, or we can also like give a quick overview of the project if there's time later.
Any questions?
I have.
Yes,
Okay, so, how do you organize all these equations in the lean project? Because I assume that there might also be other methods that generate the same equations, and it'll be hard to keep.
Yeah, that's a good question. So yeah, since I have the project open, so the equations are like defined once and for all in like these 4 files. So we have like, so they're split into 4 files for like reasons of efficiency. So like if they're split into 4 files, you can compile them in parallel. And so like these equations are all defined here. And like for example, like you have a bunch of these methods that can be used to generate like sweeping classes of like implications or non-implications at once. So those go in a folder called generated. Like for example, like these are like through some research. There should be like, you know, vampire, and yeah, like this is eGraphs, the egg thing over here. So like all of these go in separate subfolders of their own. Our code is in here. So these are the non-implications that go here. And all non-implications are tagged with the equational result tag. So that puts them in some kind of a global register, which keeps track of, you know, what's been established so far. And yeah, and that in turn is used by like various tools, like, you know, if you want to like check the status of the current project, if you want to see how many implications or non-implications have been proved so far, so you would go to your global database of equational results and like query that. And yeah, I might actually be able to, okay, maybe later, like to actually show you the actual status of the project.
This is kind of a very naive question, but like universal algebras have like a lot of fancy machinery to deal with this sort of things. So I was wondering like how much of this can be kind of, and I don't know much about universal algebra, but I feel like a certain amount of this at least is something that they would just hit with their very fancy hammer and say like, oh, this is an instance of whatever crazy categorical logic theorem, something like that. Like, I'm curious, like how this is, like, what's the landscape there?
Yeah, that's a good question. I think the aim for this project was kind of expand what universal algebra can be about, because these kinds of questions are just not feasible to do like as in traditional universal algebra. Yeah, you're not going to get universal algebra is computing by hand, 20 million implications, right? So these kinds of exploration has not been done before. But the techniques that universal algebras have been, like employing are kind of like have been guiding our the things that we have been trying, the things we have been doing. In particular, these meta-theorems. I've tried not to be too technical. Again, I've left out a lot of category theory, but you can connect this with other things that people have done in the past as well.
What's the gory version of the theorem?
So in short, okay, this whole idea of like trying to get an equation and then considering all the implications that it has, that's basically the Unedal lemma. So it's like you're trying to, yeah, that's basically it. They're trying to characterize an equation by the sets of things it can see. And I think that the main thing about the lifting magmas thing is that you can interpret the whole idea of a lifting magma. This is the nice class of magmas Anand was talking about, for which you can check just a very specific substitution to check everything. That's a particular instance of a nice class of monads, which again I don't know too much about that, but it has to do with something called Labir theories.
Yeah, that was the area I was thinking about. So.
Yeah, no, these connections exist, and you can also frame so those two things, Unedal lemma, monads, and finally you can also frame this whole idea of finding invariants, say, so things that are invariant under substitution, things that are invariant throughout the whole proof, as trying to find functors, basically. So maybe I should say something more about that. Basically, I want to say consider the poset. I haven't really used that word. So imagine the set of all laws of all equations, and then under the relationship of application, they form a partially ordered set. So that's the poset phi over there. And if you try to consider functors from this poset to the category with two elements and one, so like usually people call this two. What about this object false, this object true? So basically what you're doing here is like, if you consider functors like this, so I mean, people usually write these categories. So functors from pi to 2. This is in looking for these functors turns out to be exactly the same thing as looking for the invariants I was talking about earlier, which is kind of interesting. And I think this is a better way to think about it if you want some category theory thrown in. And it also gives you more stuff to do, because then okay, what's the structure of this category, right? Because I should say like all the functors from pi to 2, the collection of all functors also forms a category, right? And it's meaningful to us between natural transformations between those functors. And yeah, you can do a lot of fun stuff over there. I hope that answers your question.
And another way of thinking about so what we didn't actually name, or like, but what we call in the project is lifting magma families, which are basically kinds of like families of magmas where checking satisfiability of a law is equivalent to just checking satisfiability on like a particular set of elements. Like for example, enter the K over there, where like checking satisfiability in the entire thing is equivalent to checking satisfiability on the bases. So in general, like you can construct those if you have a system of like let's say a system of equalities, like you have like a set of equalities or like set of equations, such that the free magma for that set has decidable equality.
Yeah.
So yeah, so and that gives a general, like for example, if you have a system of equations which is like confluent, and so that means like there is a decision that means like the free magma has decidable equality using Knuth-Bendix. And so that gives like a sort of like systematic way of generating examples like this. But like we haven't actually, because like formalizing the theory of Knuth-Bendix and like and so on is like very difficult to do within the context of this project. We actually haven't exploited this particular strategy of producing lots of examples. And we've stuck to like the hand chosen one, like, the n to the k or like multi-sets, or like, this and
left projection, right projection, so on.